Hello guys, in today's video we're going to talk about frequency and duration acquisition using a microcontroller. In this case it's going to be an STM32. We're going to start by taking a look at this page talking about PWM signals because the working principle is the same. So here you have this signal which represents your timer. Here you have a sawtooth and we talk about up counting because we have one slope which is a positive slope. You may also have a negative slope, but most of the time we use this one known as up counting. You also have this one where you have a triangle, which is up down counting because we're going to go up and then down, and that's a different way of doing things. But for this, we're going to focus more on the up counting. So what basically happens is you have your timer, it's going to have a certain value. Like for example, let's say you choose here, it's an 8-bit timer and it's going to count from 0 to 255. And the 255 is known as the auto reload register, which means whenever you're going to hit this value, your timer is going to reset. You're going to start over again. You're going to have a new cycle again and again and again. So by using a timer, you always have to define a frequency. And the frequency, when you're in up counting, the frequency is equal to the clock of your microcontroller. Can be 16 megahertz, 80 megahertz, whatever. And you're going to divide that by a prescaler. So a prescaler is just there to divide the clock of your microcontroller even further. Can be 4, 10, whatever value you want. And that prescaler is going to be multiplied by, if you're in upcounting, the value of the auto reload register plus 1. And the plus 1 is because we start counting from 0. So we have from 0 to 255, we counted things 256 times. So in upcounting, whatever the value of your register is, of your auto reload register is, you always have to add 1 to that. And this will give you the frequency of your signal, of your timer. For the up down counting mode, you're gonna do the register. Instead of having auto reload register plus 1, it's going to be auto reload register times 2 because we're going to count from 0 to 255 here, and we're going to go down from 254 to 1. And if you add up things, you have 256 going up and 254 countings going down. If you add both, you have 510. And no matter what the value here is, you always have this value times 2. But as I said, we're not going to talk about center align here or up down counting. Just going to focus on this one. And I highly recommend you to check this page. You just have to type secrets of PWM or gisting. You're going to have that quite easily. And it's very, very well explained. You have everything talking about PWM, the differences between the up down counting and the up counting. Everything is very well explained. So let's go back to a PowerPoint. So here you have our sawtooth signal representing our timer, and this is the signal that we are trying to capture. Then we have our signal going from 0 to auto reload register and then resets every time. The frequency of a timer is its clock, the clock of the microcontroller, divided by the prescaler times auto reload register plus 1. Now, let's say we want to acquire the frequency of this using rising edges. So we have an interrupt that's going to be triggered every time it detects a rising edge. So we're going to capture one value, then the next one here. And it's going to happen again and again till we reach an overflow and then it's going to continue here continuously. And the frequency of this signal is going to be pretty much like this one, but instead of having auto reload register +1, we're going to have this value here, which is the delta CR. So the difference between these two values. Now, since we are really trying to have the frequency here, instead of waiting for the timer to reach overflow here, we can force it to reset immediately as soon as we get the first delta CR, because it's going to be always the same delta CR that we're going to get until our timer reach an overflow. So we can save some processing time by just forcing it to reset as soon as we get this one, the very first one, and then it's going to repeat. So instead of having something that will go up to this value, our timer will just do something like this every time. It's not mandatory to do that, but in some situation it can help. Now, if we are in a situation where the second value, because here we were in some, we can say, an ideal configuration where the second register that we've captured is higher than the first one. But what if we capture the second register when after an overflow? So for example, let's say here we have 255 and we had our first capture here at 200, and our timer is going to reset and the second capture will happen at 10. And if we do this minus this, we have a negative result, and that's not what we're looking for. So from the timer perspective, the value here will be 10, but in reality, the value is 255 plus 10 because we've reached overflow. So the overall formula of the delta CR is going to be the second capture minus the first capture plus the number of time we've reached overflow times the auto reload register value. So this, in this case, for example, where we have a CR2 which is higher than CR1, we didn't reach an overflow, so the value here is 0. So this is more of a general situation. And this typically happens when the signal we're trying to capture has a frequency that is lower than our minimum frequency, than the minimum frequency of the timer. Because when we have this gives us the minimum frequency we can catch in one cycle. So before reaching an overflow. In one cycle, we have this. This corresponds to the minimum frequency we can acquire, we can get. And the maximum frequency will of course be when this value is just equals to 1. So we just have clock divided by prescaler. That's the maximum frequency that we can get with our timer. And for duration, the principle is the same, but instead of having the same edges, we're going to take opposite edges, one rising edge and one falling edge. So yeah, there is no change, only the way we're going to capture the register. And of course, duration is time-based, so we'll have to invert this this frequency. Now, technically, when we are acquiring duration, it's not a frequency strictly speaking, because the frequency is really between the same edges. But you know, we can just say technically the formula is the same, so we just do 1 divided by frequency to get our duration. So now let's jump into the demonstration with the microcontroller. And you're going to see that the way we're going to capture the registers is very important. We can have completely different results. For this demonstration, I'm going to use the STM32 F303 nucleo board. And here is the configuration of my timer. I'm using timer 3 with a prescaler of 1 in up counting and with an auto reload register of 65,535, which gives us roughly a frequency of 122 Hertz. So this is the frequency of a timer, and it's also the minimum frequency we can catch in one cycle. For the capture part, I'm using the timer in so that it can capture the rising edges, so input channel polarity rising. Since this video is not really about how to use an STM32, I recommend you to go check the series of videos talking about STM32 made by Sean Himmel from GGKey. Those videos are really interesting, and you can learn a lot from them if you're new to STM32 boards. Let's go back to what's happening in the code here. So I've shown you the timer, initialization, and I'm going to use two callback functions. Here I have this one to keep track, the HAL team period elapsed callback, which is called every time an overflow occurs. The second interesting function, or should I say the main function here, is this one, the HAL team IC capture callback, which will capture our registers. So I have here some flag, I have a flag. So if the first rising edge is not captured, we capture the value, which change the value of the flag. And then if it's changed, we're gonna get else condition, and we're gonna capture the second value. And as you can see here is the formula of a delta and the formula of the frequency and the period. Here we're gonna reset the overflow count and the flag as well. So here is really where we are performing our capture and all the calculation that goes with it. This function, as I was saying in the PowerPoint, you can force this timer to reset without waiting for the overflow. As soon as you get your first delta or your second register, you capture the second register, you can force it to reset. I'm going to send the signals to the STM32 boards using my Arduino. And that's a very basic code here, but this allows me to have 3 PWM signals with different frequencies. So here's analog write, and when you're using analog write, it gives you a frequency on the Arduino Uno of 490 Hertz on these different pin, and on pin 5 and 6 you have 980 Hertz. That so you have here, and when I'm using the servo library, I'm able to generate a PWM signal with a frequency of 50 Hertz. Now there is something worth mentioning is when you're using both analog write and the servo library at the same time, you should not use pin 9 and 10 because there's some interference happening. So stick to here, for example, I'm using pin 11 for the servo. And another thing is also the GPIOs of Arduino are 5 volts, and the GPIOs of STM nucleo boards are 3.3 volts. So you need a logic level converter. And if you don't have one like me, you can use simply a voltage divider. It's just about making sure to not damage your STM board. So let's get into the demonstration. Right now I'm in debug mode, and let's see what's going on when we receive our different signals. So as you can see, for pin 3, we're supposed to have 490 and we have 491. And from time to time, you can see the value going to 97. That's probably due to the fact that the capture of the second register happens exactly at the same time as the overflow. It may disrupt things a little bit. A quick fix is to, like I said in the PowerPoint, force the timer to reset as soon as we get the second register. But let's do the other two signals. So for the 980, you can see that we have 978, 979, and still we have this another value popping from time to time, but it's fairly accurate. Now let's do the PWM signal from the servo library, which is supposed to be 50 Hertz. And you can see that there's a huge problem. It's not 50, it's not close to 50 Hertz. And now the thing is, our minimum frequency that we can get in one cycle is 122. But with our formula, we're not supposed to have this issue because of n times the overflow and all that. But we see that when we are capturing the registers, we have an issue when the frequency is lower than our minimum frequency, which is in this case 122. Okay, for now, I'm just going to do something to fix the issue with the strange value that comes from time to time. And we're going to try something else right after. So I'm going to I'm going to force the timer to reset as soon as I get the second register. I'm storing this value in this little array or buffer just so that we can clearly see what's going on. It's a little bit more visual than just having one value here. So let's start again. We still have a 27, but you can see the fact that I have enabled the timer to reset right after the interrupt, the values are not shaking as much as they used to. So I'm going to place it 1, 2, 3, 4 on the other one. You see the 591 Hertz is fixed. And for the other value, we have between 978 and 979. But at least we don't have this strange value coming out from nowhere because of whatever happens when the timer overflows. Now, the thing that I'm going to do is I will increase my prescaler. So instead of having 122 Hertz, we're going to have 12.2 Hertz. And let's see how if we get the right value for the servo. So this is a 979, 78. Still good value. We're going to do the other one just in case. 491. And the one that we're interested in right now, the servo, we have a 50 Hertz. And this is because I had to reduce the frequency. So right now, we are at 12 Hertz, which is lower than the 50 Hertz. And we are able to measure things more accurately. You can see the way we are capturing the registers right now does not really respect the entire formula. There is a way of doing things instead of capturing two registers, I'm going to capture one register at a time by making a slight change in my code. So instead of having here input this and that, what I'm going to do is I'm going to comment this one. I don't want the flag to go back to 0 and then enters here and capture this value again. What I'm going to do is I will just say the old value, the first capture register we had, will be equal to the previous. I mean, I'm just doing old capture register minus new capture register. And by using this method, we should not force the timer to reset. We should let the timer do its thing without forcing anything. So what's going to happen is from the very first time, we're going to capture this value because the flag is equal to 0 at the beginning, and then the flag will go to 1. And since we're not resetting it here, it will remain here. So every time we just capture input capture register 2. And since we are doing things in a way that input capture register 1 equals input capture register 2, which was the previous value of this, we always have this kind of new value minus old values plus this. And let's see if it make things better. So right now I'm gonna relaunch, redebug the thing. So right here we have a 50 hertz, a 491, and or 979, but we are still in with the 12.2 volts. So right here, I'm just checking that it's not worse than what we had previously. Now let's go back to what we had initially with a frequency of 122 and see how it behaves. I'll directly go to the PWM since this is really what we're interested in right now. And as you can see, where we had 27 or 22 back then, now we have our 50, and it's not even shaking, and I don't have to force anything. The value is stable. We have a 50 hertz, we have a 979 hertz, and we have our 491 instead of 490, but it's still good. So you can see how the way you capture the register has an influence on what we're doing. And you don't even need to use, with this method, you don't even need to use the maximum value of your timer. I can even do something like, I don't know, 5,000. So if you do the math here, 8 megahertz divided by 5,000, which gives me 1,600, so 1.6 kilohertz as the minimum frequency. And this 1.6 is higher than all the frequencies we're using. So let's see how it performs. We have a 491, $979, and we have a 50. So when you're using this method, no matter what your minimum frequency is, you don't, I want to say that you don't care anymore. You can use whatever you want. You will have an accurate, you're going to have accurate results. So now I don't know why when we're capturing two registers at a time, we have this lack of efficiency. I don't know. Maybe that's too much for the microcontroller to handle. I don't know. But capturing one register at a time
is definitely a better solution than capturing two at a time. So with this, we finish with the frequency, and let's do the duration. Our timer is still in rising, capturing rising edges, and that's great. I'm leaving it like that because when you're using both edge, it can start from low, from the falling edge, or it can start from the rising edge. You cannot really determine with complete accuracy how things will turn out to be. So by leaving it the initial state as rising, I know that my timer is going to start with a rising edge. And after I capture my very first value, I'm going to set the polarity to both edge. And I'll still do the same thing exactly like what I did with frequency by capturing only one value at a time. Uh, ICR1 equals ICR2. Now the difference here is I'm going to cast the clock here, which is in megahertz, 8 million. I'm going to cut, it's an integer, it's an unsigned int32. The thing is in C, when you divide two integers, your result is going to be an integer. So if I do that, since I'm going to acquire very low frequencies, things that are lower than one, my result is going to be zero, 0 point something. But because if I leave this as an int and this also is an int, my result here is going to be an int. So I will have 1 divided by 0. And when I'll be debugging, I'll always have infinity, which is not useful for what we're doing here. So for that reason, because I want to have a float, a decimal number, I am gonna, that's the reason why I cast it into a float here. I can cast either the numerator or the denominator. Here I have this counter that increments every time I capture a new register. And since I have both edge and the edges will switch from time to time, this allows me to know which one is going to be the falling to rising period or duration and the rising to falling duration by using a modulo. So if it's an odd number, I will know that if it's odd, it's going to be a rising to falling. And if it's an even number, I'm going to have a falling to rising duration. And another thing concerning these two variables that I have created, rising to falling and falling to rising, for the sake of the example, I'm going to leave falling to rising as an integer so that you can see, you will see the problem that we're going to have by leaving it as an integer compared to the other one, which is a float. On the Arduino side of things, again, here I have a very simple code where I have an output that I'm gonna turn on high for 5 seconds and low for 2 seconds. And as you can see here, the rising to falling is 5 seconds and the other one is 2 seconds. Now, as I said, I left this one as an int. And you can see our value here is 1.99. Very, very close to the 2 seconds we have here, but it's going to write 1. It will only take the integer value. So whenever you're dealing with duration, it's better to use floats. Like that, you can have all the accuracy you need. And as you can see, we have two values here, 5 seconds and 2 seconds. The rising to falling edge is 4.98 and the falling to rising edge is 1.99. And I'm going to change the values here in live. And let's put, I don't know, 10 seconds, or I mean, I can do here 2 seconds, and here I'm going to increase the rising to the falling edge. So the signal is going to be low for 8 seconds and high for 2 seconds. Right now, I'll flash my Arduino, and after some time, we're going to see the values update here. So here we have 1 point pretty much 2 for the rising to falling. So the signal is high for 2 seconds and the signal is low for 8 seconds. For those who are interested, I'm going to put a link to my GitHub in the description so that you can have access to the code. And of course, I'm going to put the version where I'm just capturing one register at a time. Thank you for watching the video and see you next time.